the important connection between unitary and Hermitian operators is through a complex exponential. So I want to play this out for you. So I'm going to start with a unitary operator. And if you are trying to understand an operator, it is always helpful to go to the eigenbasis. This is the basis where it's diagonal, and you've just got the eigenvalues down the main diagonal. Now, you're going to have some kinds of matrices possibly that aren't diagonalizable or are going to have other weirder elements, but pretty much everything you work with in physics is going to be diagonalizable and just has all the eigenvalues down the main diagonal. So if I look at u in those particular coordinates, I've learned that every eigenvalue has to be a complex number on the unit circle. So I have e to the I theta 1. I have e to the I theta 2, et cetera, through e to the I theta n. And I am going to propose a weird connection here. That I can plug this in to an exponential. And if I take e to the power of a matrix, where I have a matrix of the eigenvalues, the angles, sorry, not the eigenvalues, just the angles of those eigenvalues down the main diagonal, that is going to recreate u. So you might have seen before how we evaluate a matrix plugged into an exponential. Now, e to some exponent like this doesn't initially make sense, but it will make sense if you treat it like a power series. You can't really raise a number to something a matrix number of times. That sense of exponentiation doesn't make sense. But if we do the power series, where this becomes x to the n over n factorial, now we can do this. Now everything I plugged into my exponential goes right here to the x. And this becomes I've got 1 over n factorial, and all this stuff is raised to the n power. I've got I to the n, and I have that matrix full of angles to the n. Now, the nice thing is, when you multiply diagonal matrices, you don't have to do matrix multiplication. All the numbers on each spot in the diagonal multiply together. They don't mix. So if I raise this to the n power, theta 1 gets multiplied by itself n times. Theta 2 gets multiplied by itself n times. And that just repeats. If you're not sure on that, write out a diagonal matrix squared, and you'll see it happen. If you just do it for yourself, you're going to get it intuitively and know what to do every time. So now, I'm no longer doing matrix multiplication. And sorry, I had some bad notation here. I treated this as 1 through n. I'm also doing my sum as 1 through n. Let me change this to m's so there's not a chance of getting those mixed up. Now that I'm no longer doing matrix multiplication, I can just add these together. So every entry of this matrix, as we are adding all the matrices in a series, the numbers in that matrix entry become their own little infinite series. So now I have a matrix where every entry is 1 over m factorial I to the m, theta 1 to the m, down to the same thing going on in the last entry. And that is just the definition of e to the x as a power series. Every one of these is going to become e to the I theta 1, e to the I theta n, and that is just the u that you started with. And importantly, this matrix of angles, this is all real eigenvalues, and this is Hermitian. If I dagger this, I transpose it, I flip it across the diagonal, nothing changes, it's all on the diagonal. I complex conjugate it, nothing changes, it's all real. This is equal to its own dagger, so this has to be Hermitian. So I can do this for every unitary matrix. Every unitary matrix is secretly e to the I times a Hermitian matrix. Now we can connect this to the Schrodinger equation. And by sheer dumb luck, I have been calling H for Hermitian the whole time. H is also going to get to stand for Hamiltonian, and it just so happens that those are both H's. So if I have a quantum mechanical wave, and I want to move this forward in time, I'm going to have, for quantum mechanics, that length equals probability. So if I want to conserve probability, if I want to make sure that all of my probabilities add up to 100%, that means I have to conserve length. That means that I have to use a unitary transformation. If I'm going to move my wave forward in time, whatever I do, the probabilities better still add up to 100. But we have learned that for every unitary transformation, that's going to be like e to the I h, where h is Hermitian. So as I move my quantum mechanics wave forward in time, it's going to look like this. And this is exactly what obeys the time-dependent Schrodinger equation. It just comes from the fact that you've got to move forward in time and conserve probabilities, and the thing that does that is e to the I Hermitian. Now, from Noether's theorem is going to link conservation of energy to time. Moving forward in time is a symmetry, and the thing that is conserved from that symmetry, the conserved charge that comes with that transformation, is the Hamiltonian. So, through some extra theorems, we learned that this particular Hermitian operator is indeed our Hamiltonian, is our energy. So, with this framework, a lot of fundamentals in quantum make more sense. These are the principles that hold it together. And once you know that, you can start putting together some of these abstract ideas in quantum much more coherently.